We are going to talk about some of the key components in Kafka. A topic is where data is stored in Kafka and is split into partitions. Each partition can be replicated across multiple brokers for fault tolerance. You can think of a topic like a folder and partitions like sections in that folder where data is stored and managed. Partitions allow Kafka to scale horizontally, meaning multiple consumers can read from different partitions at the same time. But what happens if a broker fails? This is where replicas come into play. Kafka replicates each partition to ensure there is always a backup. These replicas are stored across different brokers, providing fault tolerance. Let's see how this works when we have a single partition. In this case, the topic has just one partition, which is then replicated. The partition 1, has two replicas. Replica 1.1 is stored on broker A, and replica 1.2 is stored on broker B. Replica 1.1 on broker A is the leader, handling all read and write operations. If broker A fails, replica 1.2 on broker B will take over as the new leader. Now let's take a look at how Kafka works when a topic has more than one partition. As we discussed earlier, a topic is divided into partitions to help Kafka distribute and scale data processing. In this case, the topic is split into two partitions, which means the data is divided into two separate sections. These partitions allow multiple consumers to read from the topic in parallel, improving performance and scalability. Each partition, just like before, has replicas to ensure fault tolerance. If one broker goes down, the other brokers can still serve the data. In this diagram, we see that partition 1 is replicated across broker A and broker B. Partition 2 is replicated across broker A and broker C. This distribution ensures that even if broker B or broker C fail, the data from partition 1 and partition 2 will still be available from their respective replicas on broker A. This setup increases both fault tolerance and the ability to scale as more partitions mean better distribution of the data across brokers. In Kafka, brokers are the backbone of the system. Think of them as the intermediaries between producer and consumers. When producers send messages to Kafka, they go directly to the brokers, which store and manage these messages. The brokers also handle distributing these messages to consumers. They make sure the data is replicated and persisted, ensuring reliability. Let's talk about the two modes of metadata management, Zookeeper and KRaft. Right now, Kafka relies on Zookeeper. Zookeeper is like a coordinator that ensures the brokers are working together, managing metadata such as controller election and topic configurations. It's essential for keeping everything synchronized in a distributed system. Zookeeper will soon be replaced by KRaft mode, which is a self-managed system where Kafka handles all the metadata internally. This will simplify the architecture and improve performance. In a Kafka ecosystem, producers and consumers are the key players. Producers send data to the brokers, and consumers retrieve that data from the brokers. Kafka uses partition to split the data in a topic, and brokers manage these partitions. The use of partitions ensures that the load is distributed across brokers, improving performance. Let's now take an example. Imagine we have a payment topic. This topic holds transaction data, such as payment process through an application. Like on Kafka topics, the payment topic is divided into partitions. In this case, we have only one partition, and replica 1.1 on broker A has been elected as the leader. Replica 1 true on broker B is for fault tolerance. The producer sends data to the replica 1.1, which is the leader for this partition. On the consumer side, we have a single consumer that reads payment data from replica 1.1. In this setup, because we only have one partition, we can only have one active consumer instance. If you spin up another consumer instance, it will be idle. Now let's extend this setup to a payment topic with two partitions. Each partition still has replicas for fault tolerance, but now we can handle more data in parallel. For partition 1, replica 1.1 on broker A is the leader, while replica 1.2 on broker B provide fault tolerance. For partition 2, replica 2.1 on broker B is the leader, and replica 2.2 on broker C is replica for fault tolerance. The leader for each partition is the replica that actively handles both writes from producer and reads from consumers. When the producer sends payment data, it divides the workload across both partitions. For example, odd number transactions could go to partition 1 and even number transactions to partition 2, ensuring better distribution of load. On the consumer side, since there are two partitions, we can now spin up two consumer instances, each reading from one partition. This allows us to process data in parallel. If you only have one consumer, it will read from both partitions. But adding a second consumer enables each one to take ownership of a specific partition, maximizing efficiency.